everyone. Thank you for coming to this session. I'm Jun. I'm a senior data scientist from Lyft. In my everyday work, I use machine learning to solve business problems. So I spend a lot of time looking for new technologies and tools that can improve my machine learning productivity so that I can focus on solving more problems. And today, I want to present this distributed hybrid parameter tuning library called Fugue-tune. So if you also work with machine learning and there's a parameter in your model, then this talk is for you. And before we start, I want to give you a quick intro to what is Fugue-tune, as we're going to do a lot of demo with this library. So tune is an abstraction layer for general parameter tuning. It has integrated popular hyperparameter tuning libraries such as Optuna and Hyperopt. It has also integrated machine learning lifecycle management frameworks such as MLflow, and weights and biases is in progress. So Tune provides a scalable and simple interface on top of all of these great frameworks. And in addition, Tune is built on Fugue. Fugue is an abstraction layer of distributed computing. So with Fugue, Tune can seamlessly run on any backend, such as Spark or Dask. In today's presentation, I will first give an introduction to the hyperparameter tuning problem in machine learning. And then I'll discuss some of the common pain points from a data scientist point of view. I'll then talk about how those pain points are addressed by Fugue-tune. Throughout the presentation, I'll walk you through some basic usages, such as constructing a hybrid search space, which is an entirely new concept we introduced, and as well as some advanced tricks, such as distributing the tuning job on Spark and monitoring the result in real time on MLflow. To start, let's recap the problem of hyperparameter tuning in machine learning. Hyperparameter tuning plays a critical role in the machine learning workflow. Almost every model in industry today has hyperparameters that must be set in order to help the model generalize to the problem and the data set. If we use a suboptimal set of hyperparameters, that will directly result in suboptimal model performance. The essence of hyperparameter optimization is very simple. So from a search space, for example, on the left, we want to find a set of hyperparameters that could maximize or minimize an objective function. For example, on the right, which could be a machine learning objective function that takes the model hyperparameter as input and output a score on the validation set. So this is very straightforward and simple, right? However, to realize such a straightforward tuning flow may be extremely cumbersome today. Let me give you a concrete example that is common in every model developer's work. So this problem is very simple, but there's no elegant solution so far. So Han is working on the California housing price prediction problem on Kaggle. By the way, Han is the developer of Fugue-tune, and Han is here if you have any questions. So Han is working on this California housing prediction problem, and he looked over the discussion board on Kaggle and saw that many people are using XGBoost and LightGBM. So naturally, Han, like many of us, want to say, then why don't I try both of them and take the best result? So Han want to do a tuning on both of the models, so to get the best result. Since XGBoost usually takes longer to train, so Han decided to use Gray Search for XGBoost and Bayesian Optimization for LightGBM, so they can finish probably in the same time. I'll pause here for a second, and let's think together. If you were Han, how would you going to design the search space and the tuning flow of this problem? So basically what we want is we just want to train two models. and we want to tune the two models with different tuning methods. That's all we want to do. And I will think out loud here for my solution. So first of all, no matter what tuning framework to use, we need to define an objective function to optimize, similar to the one here. In this problem, I need a function that trains and validates the model, then outputs a metric score to measure the model performance. And the input are different modeling algorithms and hyperparameter sets. So in this example, we are outputting the average of mean absolute percentage error across the validation sets. Not too bad so far. And next is to define the search space. So intuitively, I need a search space for XGBoost, where I do gray search, say on N estimators. And then I want another search space for LetGBM, where I want to do a Bayesian optimization on, say, N estimators. And finally, I'll use some optimizer to find the best parameters from the union of these two search spaces to get the model that gives me the best result. So this is really simple, right? Then let's try to code this out. So as you can see, even using the simplest existing tuning interface, Optuna, the code will be this long. And this is because, first, different tuning methods are exclusive to each other. So users need to define separate objective functions to use more than one method. And second, to do gray search, parameters have to be declared twice in different ways. But going back to our original problem, all we want to do is just this little piece. So couldn't there be a simpler and more elegant approach? And let me introduce Fugue-tune's solution. On the left side, we have the code defining the search space and optimization flow using Optuna. On the right side is Fugue-tune's code. And note that in Tune's approach, we're also using Optuna for Bayesian optimization. So these two code snippets here are doing exactly the same thing. But we can see that the Fugue-tune's code is much simpler and more intuitive. In Tune's code, the model search, gray search, random search, and Bayesian optimization, they can be combined intuitively into one space using simple space operations. For example, here we used the plus sign to take the union of the two search spaces. And also, there's zero redundancies on defining any parameters. So what makes Tune's interface so simple? And what else can we do with this space operators? The secret is in Tune's definition of spaces. Apart from manual tries, there are three main methodologies to find optimal hyperparameters that are popular today. Gray search is the most commonly used tuning method. It exhaustively traverses through all the set of user-specified parameter values, and the result is deterministic. So it is good for categorical parameters, such as modeling methods, or anything we want to make sure to traverse through all the options. However, gray search is extremely inefficient because the computational complexity will increase exponentially with the number of parameters. In Tune, gray search is defined using the keyword grade. Random search, on the other hand, gives users the control on the number of total iterations. It can outperform gray search, especially when only a small set of hyperparameters are affecting the final model performance. However, because each guess is independent from the previous one, it normally requires a large number of samples to achieve a good result, which may be limited by the time and the resources. And in Tune, random search is defined using rand and choice with a specified number of samples. A third well-adopted tuning method is Bayesian optimization. Different from random sampling, Bayesian optimization builds a probabilistic surrogate model for hyperparameter itself, and it intuitively makes the next guess. It iteratively makes the next guess based on the previous observations. So Bayesian optimization was proven to be able to achieve a better result in fewer evaluations. However, its intrinsic sequential process, the iterative process, cannot be distributed. So in some cases, it may take longer time to finish. In Tune, Bayesian optimization is defined using the same keywords as random search without specifying a number of samples on the space. And here comes the amazing part. We're putting different types of space together. So Tune allows users to define hybrid search spaces using simple operations. In this example, we define a random search space for the parameter A, a gray search space for parameter B, and then we use this plus sign to take the union of the two spaces. And in addition to the union, we defined a Bayesian optimization search space for parameter C. And we use a star operator to multiply this Bayesian optimization to the union of the two spaces as a second layer of optimization. On the right side, we can see in the generated search space, we have two samples for parameter A. They're from the two samples of the random search. And we have two samples for parameter B from a gray search on two options. And all of them are followed by a Bayesian optimization on parameter C as a second layer of optimization. Well, it's okay if you haven't got a fully got idea yet. Let's do a quick demo on the space operations. Actually, let's see if we can do a live demo here. Cool. So Tune has two space operators, the union operator, the plus sign, and the cross product operator, the star sign. I'll do one example for each, and then finally I'll put them together. Let me know if the font is big enough for everyone to see. Cool, thanks. So starting from the star operator, this example is similar to the California housing problem where we want to train three models, like we want to use three different modeling algorithms at the same time, but we want to tune them using different methods. For example, we want to use grid search for XGBoost, random search for LightGBM, and Bayesian optimization for CatBoost. So in this case, we can just define three search space, each for one of the model, and then simply use the plus operator to add these three spaces together to take the union of the search space. And then in the generated search space, we can see that we have two samples for XGBoost, and they're coming from a gray search on two options. And we have three samples for LightGBM. They're from randomly choose three samples from the given range. And lastly, we have one sample for CatBoost on Bayesian optimization. So this is union of the spaces. And next, let's see what if we want to apply mixed type of parameter tuning methods to one modeling method. So for example, now let's say we figure out LightGBM works the best for our model. So we want to look into LightGBM and fine-tune its parameters. So in this case, we could, in the new search space, ping the model method to be LightGBM. And similarly, we can use the search space definition to ping any other parameters. We want to fix them at a certain number. For example, your N estimator may be limited by the online inference computation constraint. So I can only take 100 N estimators. So I ping it to 100. And then we may want to use gray search for the boosting method. So we can make sure we will definitely try both of them during the tuning process. And then, for example, we may want to use random search for feature fraction because I know it's less important to my problem, so I don't want to spend too much computational resource on that. And I think learning rate is very important. So I want to fine-tune learning rate, so I want to do a Bayesian optimization on learning rate. And here, note that because for Bayesian optimization, we don't want to specify the sample outside the space. Otherwise, it will be recognized as a random search. So Bayesian optimization is defined in a separate search space. And now we want to put these two spaces together, and there can be more spaces, like static space, one gray search space, and random search space for this model. But putting them together, we just need to use this star operator to multiply them together. And here we can see in the generated search space, we have 4 samples. 2 of them are from, they're from the 2 gray search cross product with the 2 samples of the random search. And each of them has a Bayesian optimization applied on learning rate. So this is cross product. And finally, let's put them together. So really, we can use these 2 space operators to generate any type of hybrid search space we want. So as an example here, say this time we want to, again, try out all 3 modeling methods. But we want to tune their common parameter and estimators and use Bayesian optimization for tuning all of them. So we may need to repeat the code 3 times before, but with tune, we can just define 1 Bayesian optimization space for N estimators and 3 model space for each of the modeling method. And finally, we use the plus sign to take the union of the model space and then multiply it by the Bayesian optimization space on the common parameters. And then if we run this, it will give us a search space of 3 samples. They have different modeling method, and all of them has a Bayesian optimization applied to N estimators. So this is space operations and how to construct hybrid search space with tunes, space keywords and operators. And next, let's talk about the other important part, distributed tuning. So far, our tuning flow has already been more efficient. But if we want to execute the tuning flow, it may take forever for one single machine to run. And the solution is parallel computing. But to do it right, it will require advanced knowledge and amount of time to put into get familiar with the distributed computing. But recall that tune is built on Fugue, so we can seamlessly run all the tuning jobs distributed without any extra code because Fugue will handle all the backend logics. So for example, for the California housing problem, say now we want to distribute the job with Spark. And all we need to do is just add a parameter inside the suggest method, and everything else will be handled by Fugue. It will parallel everything that can be parallelized. And we don't need to write any Spark code or Dask code, or we actually don't even need to know what is Spark or Dask at all. In the next section, I want to show you some other advanced knowledge of Tune to further increase our modeling productivity. So starting from the result monitoring, it is really important to monitor our tuning process in real time, especially if we're doing parallel computing. But again, that requires in-depth parallel computing knowledge. And also, it will require some code change. But again, this can be achieved easily through customizing just one parameter in Tune's suggest function. So recall that Tune has integrated MLflow. So for example, now I want to monitor my tuning job using MLflow. All I need to do is to set the logger to be MLflow in the suggest method. And in addition to the highly abstracted EOI, the logging is also highly organized. So normally when we're using MLflow, I believe there are a lot of MLflow customer users here, you will see a list of all the runs in this experiment summary. It was great, but it could be messy if we're running thousands of trials all together. In Tune, the logging was designed as, for each suggested method we call, there will be a parent run logged at the higher level. And then if we expand that parent run, we can see all the subruns. Those are the subtrials in the suggested method. And at real time, the best metric from all the subruns will be updated to the parent run. So we can really just look at the parent run to monitor the entire tuning flow. And before the next demo, another thing is really easy to achieve in Tune is to switch between different libraries for Bayesian optimization algorithms. Because Tune integrated Hyperopt and Optuna, so if we want, we can switch between these two libraries seamlessly by just changing one parameter. So we can benefit from all this great framework without changing a single line of code in our modeling flow or objective function or tuning flow. And we have seen a lot of great features. Let's see how to apply them to maybe our California housing problem. All right, so recall that in the California housing problem, we want to train both LetGBM and XGBoost. And we want grid search for XGBoost, Bayesian optimization for LetGBM. So here we have already defined the objective function and the two search spaces. And before we get to the tuning part, let's quickly check the baseline score of the two models to get a sense on what the performance would be with the default parameters. So it looks like they're giving similar results on point 18 for both of the models. And now let's get to the tuning part. So fundamentally, what we want to do about the tuning is we want to evaluate the objective function over a search space we defined. In this case, is a union search space of two models. And we probably want to try a specific method for Bayesian optimization. Additionally, if the scale is large, we probably want to distribute the job on Spark. And finally, it would be great if we can monitor the result with say, MLflow. So I'll pause here again, and let's think what normally we may design this workflow or this tuning flow using existing libraries. Or let's think about what do we want this tuning flow to look like. And I'll start to type my answer here. So I'll just go over this task list. The first thing I want to do is to evaluate the objective function, which I have defined above. So I'll put the objective function name here. And then I want to evaluate this over a search space I defined. In this case, I have two search spaces, one for XGBoost and one for LetGBM. And recall that since we have two spaces, we can just use a plus sign to take the union of them and put them all together into this suggest method. And then I want to apply Optuna for Bayesian optimization. So I'll say local optimizer is Optuna. And I'll probably give a max iteration number. And then I want to distribute this job on Spark. So I can say execution engine, please use Spark to pass in the Spark session. And finally, I want to log the result using MLflow. So I'll choose MLflow as the logger. And let's run this. So as you can see, we are achieving so much things with just calling one function. This is really just one line of code. So it's super intuitive and simple. And by the way, here we're using the suggest for non-iterative objective method. If you're doing deep learning, you can use the suggest for iterative objective method. So now we start the tuning job, and it's with Databricks. I really like how easy we can monitor the Spark jobs. We can also monitor our result in the experiments. So if we click into the California Housing Notebook, we can see the first one is the most recent run we just kicked off. It's still running. So let's look into a previous run I did yesterday. We can see so these are all the parent runs. Each of them is corresponding to one run of the suggest method. And the best result is logged at the highest level. If we want to look into details, we can expand that, and we can see here we have 4 subruns. 3 of them are for XGBoost on a gray search space, 100, 200, and 300. And there's one for LightGBM. It has a Bayesian optimization. And we can click into the subrun to monitor how this metric was improved over time by Bayesian optimization. And if we go back to the summary, so this one is still running. If we go back to the summary, we can just look at the best result from the parent row. So the winner is, in this case, is LightGBM with a score of around 0.17. So at the end of this presentation, I want let's look at one interesting example of the real case application of Fugue-tune on a forecasting model using Greykite. Greykite is a time series forecasting library developed by LinkedIn. And we choose Greykite here for 2 reasons. One is this is a fairly new open source library, meaning that it has an entirely new look of objective function. And second, Greykite is an additive forecasting library, so it is very flexible. We can tune a ton of parameters, which make it a perfect case for demonstrating tuning jobs. And in this example, we are going to forecast the number of wiki daily log page views for one of the greatest football quarterback player, Peyton Manning. The data frame here contains data from 2007 to 2006. And there are 2 columns, the time column TS and the value column Y. The data value ranges from 5 to 12. And we'll be training and evaluating a forecasting model using time series cross-validation. And the last year of the data will be reserved as the testing set. So recall that we said Greykite is really flexible model. There are tons of parameters to tune. Here's a list of common parameters we can tune in Greykite. So there are date-time derivatives, growth, trend, seasonalities, and events like holidays. And in this case, could be Super Bowl dates. So that's the problem setup. And let's see what the code looks like. So starting from the objective function, as we can see, this is, oh, by the way, this demo is meant to show applying tuning flow to a complex objective function, the huge search space. So you don't need to read every single line of code. I'll highlight where it's most related to our topic. So this is the objective function for this forecasting model. And it's a standard one. I didn't try to add everything to it. As you can see, it's super detail-oriented because of the flexibility of Greykite. But that is totally fine. So with Tune, we can define the objective function using just native Python language. There's no certain rules or limitations or how your objective function should look like. All we need is have this function to output a model score so we can evaluate the result. And all the rest will be converted by Tune to be Tune compatible. So this is really great because this means I don't need to rewrite my work to use Tune. And next, let's see how to define the hybrid search space. Again, as we can see, there are so many parameters here. There are seasonalities, change points, and events, and there are more. But that is totally fine. We can still define them intuitively, and also we can apply mixed type of tuning methods to different parameters. For example, here we're using Bayesian optimization for seasonalities, as well as regularization strings for the change point detection algorithm. And we apply grid search for the number of days before and after holiday. So everything is really organized and intuitive. And the best part is with just calling this one single function, we can tune this model, distribute it on Spark, and we can monitor this tuning job effortlessly using MLflow. I don't need to write a single more line of code. And similarly here, if we go to experiments, we can, at real time, track the progress of this tuning. So this one may take a little bit time. Let's again look into one I ran yesterday. So if we look into the sub-trials, we can see for each of them, we can clearly see the objective metric. And there are also metadata if we want to log them easily, and all the associate parameters. So to summarize today's presentation, we have covered 3 major parts of distributed hybrid parameter tuning: the definition and construction of a hybrid search space, the distributed model evaluation and result monitoring, and lastly, how to apply everything to a general but complex and general ML problem. So I hope you are excited to try this out on your own work. And lastly, both Tune and Fugue, they are open sourced. Feel free to install them with pip install Tune and pip install Fugue. And everything we demoed today are available online. The demo videos are also available on YouTube. Please feel free to check them out. Thank you so much for listening. I'm happy to take any questions.
Do we have any questions for our speaker?
That was a very interesting talk. Thank you. I do have a question regarding the hybrid tuning example that you showed, especially around the same algorithm, for example, XGBoost, but you basically chained these different hyperparameters together using different types of space, like random forest, one of the hyperparameter. But the thing I want to ask is about the learning rate, which is on the using a Bayesian search, right? So, when you search, tune these hyperparameters, they come as a set, right? So I'm just trying to understand how do you basically tune everything together while only one of the hyperparameter is using Bayesian search, because the hyperparameters are not really independent. And Bayesian search is basically, looking at the last try. So it's sequentially run. So I don't know if you understand my question or.
Yeah, are you referring to for example, something similar to this second example here?
Yeah, so that's exactly the.
That's a great question. So, that's really the essence of hybrid search space. So Bayesian optimization is applied as a second layer of optimization, and the first layer is either grid search or random search or a static list of scores that those scores are fixed. And then Bayesian optimization was applied to the rest of the parameters.
I had one other quick question. With Bayesian optimization, you're saying that it would have to run iteratively rather than in parallel. So like when you include the Spark option, like how does that work? Is it still able to run in parallel? Like what part runs in parallel and then what part runs iteratively?
Yeah, that's also a great question. So for Bayesian optimization, as we mentioned before, it cannot be parallelized. That's the kind of drawback of that. But the grid search and random search can be parallelized. So for example, if we have space like this, then the parallelization will goes like the sample, if there's Bayesian optimization, it will stay in a single machine to finish the Bayesian optimization part, because Bayesian optimization cannot be parallelized. But these 4 samples can be parallelized running on 4 machines.
Awesome. Let's give it up one more time for our speaker.